In this video, we'll wrap up a problem that involves a flow network or a street network in which cars enter at different rates and exit at different rates. And we do have some data in terms of on the outer streets being the streets that lead basically out of this little square network here. And so we took some measurements. We find out that these are the inflow rates, and we want to determine, based upon that, how many cars are basically making turns at different points. So of the 640 that enter into intersection D, and how many of them come through intersection D heading westbound. And so we have this information. We'd like to determine what these variables are. Maybe we only have so many meters available to test these flow rates, and as a result, we want to try to kind of extrapolate based upon that. So this is what we've done. This is the data that we've collected, and the question is, based upon that, what can we determine? So we know that at any intersection, the number of cars flowing in total has to equal the number of cars flowing out. So in intersection D, we would have that 640 plus x4 has to equal the cars flowing out, so the 310 and the x1 flowing out there. We just don't know how many are flowing out heading westbound. And similarly, we know that in intersection C, it must be the case that 390 plus x3 has to equal 600 plus x4. And again, now we can look at intersection B and we can say, well, x2 plus 520, or 520 plus x2 has to equal what's coming out, so 480 plus x3. And finally, now for intersection A, we can say that 450 plus x1 has to equal the outflow, which is going to be, let's see, 450 plus x1 has to be x2, or 610 plus x2. And now what I can proceed to do is to get this into standard form. So for the first equation related to D, I can write this a couple of ways. I can say negative x1 plus x4 equals, so basically I move the x1 over, and I'm going to move the 640 over. And if I do that, I get negative 330. And you can also do the opposite. You can move the x4 over and the 310 over if you'd like. I'm just trying to stick with this side and leave everything that's get everything on that side. So similarly here, I can say that x3 minus x4 has to equal 600 minus 390, which would be 210. And for the third equation, I would have that x2 minus x3 equals 480 minus 520, which would give me negative 40. And finally, x1 minus x2 has to equal, that's going to be 160, which is 610 minus 450. So now I'll build my my augmented matrix, and so I have to just make sure I keep track of x1 through x4, so maybe it would be helpful to just write these down so I know which coefficients I'm dealing with. So this guy has negative 1x1, positive 1x4, has 0x2, 0x3s, and then the constant is negative 330. Here I have 1x3, negative 1x4s, 0x2s, 0x1s, and 210 as the constant. Here I have 1x2, negative 1x3s, 0x1s, and 0x4s, and then a constant of negative 40. And here I have 1, negative 1, 0, 0, 160. Okay, so I want to get this into reduced row echelon form. So my strategy is, first of all, to focus on the first column. And what I think I'm going to do here is I'm going to go ahead and try to work this by hand as far as I can, since I'm only dealing with ones and nice decimals here. I'm going to first of all take 1/2 of row 1, so that I get that, excuse me, not 1/2 row 1, what am I talking about here? I'm going to take negative 1 times row 1, and I'm going to leave it in row 1. So you don't really have to do this, put it in row 1 notation, but that just emphasizes that all you're doing is you're multiplying the row by negative 1 and not moving anything else. So this would make it 1, 0, 0, negative 1, positive 330, and then 0, 0, 1, negative 1, 210. And further, we'd have 0, 1, negative 1, 0, negative 40, and 1, negative 1, 0, 0, 160. Okay, So we would proceed in this fashion, and the first thing I'm going to do is try to cancel out the row 4. So I'm going to do that. I can't do that with rows 2 or 3 because there's a 0 there, so regardless of what I multiply those rows by, I won't be able to cancel out that 1. So I'm going to take -1 times row 1, and I'm going to add it to row 4, and leave that result in row 4. So that would give me the same matrix, 1, 0, 0, -1, 330, 0, 0, 1, -1, 210, 0, 1, -1, 0, -40. And now in this row, so I have to take -1 times 1 and add it to 1, which is 0. And -1 times 0 plus -1 is still -1. -1 times 0 plus 0 is 0. -1 times -1 is 1 plus 0 is 1. And then I have to take -1 times 330, which is -330, plus 160 will give me -140, -170, I believe. Okay, so now we want to focus on the second column. Now, if we remember the reduced row echelon form, the diagonals should all be 1. Right now, the way I have this set up is this diagonal going this way is not going to become what I want it to become because of the fact that I have actually a 0 here. So I've got to make that a 1, and I'll do that basically by switching row 2 and row 3. So I'm going to switch row 2 and row 3 so I can get that leading 1 in the second row. So this will give me 1, 0, 0, -1, 330. And then 0, 1, -1, 0, -40. So I'm swapping row 2 and row 3. And then row 3 becomes 0, 0, 1, -1, 210. And 0, -1, 0, 1, -170. Okay, so what am I going to do now? Well, I'm going to take -1. I'm just going to take row 2 and add it to row 4, because this is a positive 1, this is a -1, so the positive 1 will cancel out the -1, and I'm going to leave that result in row 4. Doesn't seem like there's enough space for this, huh? Okay, so I'll have 1, 0, 0, -1, 330, and 0, 1, -1, 0, -40, 0, 0, 1, -1, 210, and finally, I will now have, because I'm adding row 2 to row 4, that will cancel out, well, there's already a 0 here, so 0 plus 0 is 0. 1 plus -1 is 0. -1 plus 0 is -1. And 0 plus 1 is 1. -40 plus -70 is -210. Okay, so far I'm good on my first column, I'm good on my second column. Now I want to focus on the third column, and I want to make these two zeros, and I want to make this guy a 0, so I start to progress with the 1s across the diagonal, 0s everywhere else. So it doesn't matter whether I want to take away that -1 in the second row first, and maybe that's what I'll do. So I'll take, let's see, I guess I could just add row 3 to row 2 and put that result in row 2, because 1 plus -1 is 0. So we proceed, and again, you can do this in the calculator by, I want you to understand how to do this. Eventually we'll use the RREF button, but part of this class is learning how to do this. So we're going to take row 3 and add it to row 2, so that means I'll have 0 plus 0 is 0, 0 plus 1 is 1, 1 plus -1 is 0, -1 plus 0 is -1, 210 plus -40 is 170. And at the same time, I think what I'll do in one step is I'll also take row 3 and add it to row 4. And leave it in row 4. Because if I add 1 to -1, I'll 0 that guy out as well, and I don't have to multiply by any constant. So I'm just going to write down row 3 since I'm not changing row 3. But now 0 plus 0 is 0, 0 plus 0 is 0, 1 plus -1 is 0, -1 plus 1 is 0, and 210 minus 210, wait a minute, I think I made a mistake here. No, I think we're okay, because we added row 3 to row 2. So 210 plus -210 is 0. Now wait a minute, something weird has happened here. I don't have a leading 1 here. I've suddenly turned all of my coefficients and my constant into zeros in row 4. So I can't go any further because now my process would be, well, I've got the correct leading coefficients in rows 1 through 3, but now the goal would be to use row 4 to cancel out the negative ones above it. I can't do that because there's nothing I can multiply 0 by to get a positive 1 to cancel out the negative ones. So unfortunately, now we have to stop because there's nothing else we can do. Again, the fourth row is all 0, so it's useless, and there's no way that I could get the ones along the diagonals. Because remember, I want to be able to say that x1 equals blank, x2 equals blank, x3 equals blank, but I have 0 x4s in the fourth row. So that's rendered completely useless. So what do I have to do? Well, I've taken it as far as I could. My columns 1 through 3 are fine, but there's nothing much I can do with column 4. You might say, well, can't we cancel out some of these negative ones? And you can, but if you start taking constant multiples of any one of the rows and adding them to the other, because there are ones in positions along columns 1 through 3, you'll start introducing those into the rows either above or below. So if I add this row, -1 times row 1 to row 3, then suddenly I'll get a -1 in this spot, and I'm kind of working backwards at that point and hurting myself more than I'm helping myself. So the best we can do at this point is to read off what we have right now. So right now we have that x3 minus x4 has to equal 210. It must also be the case that x2 minus x4 has to equal 170. And it also must be the case that x1 minus x4 has to equal, let's see, x1 minus x4 has to equal 330. Now, what do we notice that's common across all of these equations? Well, they all rely on x4. So I can write each one of these, x3, x2, and x1, in terms of x4. So x3 would be equal to 210 plus x4. x2 would be equal to 170 plus x4. And x1 would be equal to 330 plus x4. Now the question is, what is x4, right? Well, that was totally up to us. That was totally unexpected that x4 is undetermined. In other words, unless I know x4, I cannot determine the values of x1 through x3. Practically speaking, if we go up to our graph, unless I know this particular value right here, where is it, x4, unless I know how many cars are flowing from intersection C to intersection D, I can't determine x1 through x3. But as soon as I do know x4, I can immediately solve for x1 through x3. So because all three of these flow rates depend on x4, we say that x4 is a free variable. And this type of system is called an underdetermined system. In other words, anytime you have you don't have enough information, we call underdetermined. So maybe I should respell that. Underdetermined. And that's not necessarily a bad thing. If I can get one piece of information, if you can tell me something about x4, then I can figure out the remaining values. And you can see here that x4 can pretty much be anything because of the way this is structured. So if we look back at the network, x4 really has no limits, which is kind of an odd thing to say, right? Because we can essentially make it whatever we want, and then use that to give us information about x1, x2, and x3. Let me just check here that make sure all those are supposed to be -1s. So we added row 3 to row 2. Yeah. So we have all those -1s. So anyway, these are all plus x4s. So we call this. So at this point, what would we do? Well, if you gave me a value of x4, I could produce more information. We have to conclude that there's not enough information. The system is underdetermined. I think I just wrote undetermined, but it's underdetermined. Okay, well, one other situation that arrives, if there's an undetermined system, there's also such a thing called an overdetermined system. Overdetermined system. And this happens when there are, this may happen when the number of equations is greater than the number of variables. So let me give you an example. Let's say x plus y equals 10, 2x plus y equals 15, and x minus y equals 3. Okay, so if I set this up in a matrix, and this one will be fairly quick to do, so this one shouldn't take as long. 1, 1, 10, 2, 1, 15, 1, negative 1, 3. And now if I took, kind of again worked on the first column, I took negative 1 times row 1 and added it to row 2, and left that result in row 2, I would get, let's see here, so I'd have 1, 1, 10, negative 2 times that, because I need to cancel out the positive 2, so this would give me 0. Negative 2 times 1 is negative 2, plus 1 is negative 1. Negative 2 times 10 plus, negative 2 times 10 is negative 20, plus 15 is negative 5, and negative, and that, oh, sorry, and this column would be left alone. A row would be left alone. And so now I want to take negative 1 times row 1, add it to row 3, and leave the result in row 3. And that would give me 1, 1, 10, 0, negative 1, negative 5. And negative 1 times 1 is negative 1 plus 1 is 0. Negative 1 times 1 is negative 1 plus negative 1 is negative 2. Negative 1 times 10 is negative 10 plus 3 is negative 7. And now I would go ahead and work on the second column. So basically I want to take negative 1 times row 2. So I make that coefficient, the negative 1, into a positive 1 and leave that result in row 2. So that'll give me 1, 1, 10, 0, 1, 5, and 0, negative 2, negative 7. Okay, well here's what I'm going to do next. I think I'm going to go ahead and, so since I'm operating on the second column now, since I've got the 1, 0, 0 in the first column, I think what I'm going to do is I'm going to work on getting rid of the third row, zeroing that out. So this could lead into some dangerous things. So what I'm going to do is I'm going to take 2 times row 2 and add it to row 3 and leave the result in row 3. And what that'll allow me to do is cancel out that coefficient. So 1, 1, 10, 0, 1, 5. 2 times 0 is 0 plus 0 is 0. 2 times 1 is 2 plus negative 2 is 0. 2 times 5 is 10 plus negative 7 is 3. Now the reason I did that first is to jump to the conclusion, which is look at what the third row is now indicating. So I've got the kind of the reduced row echelon form here, and I can proceed, and not everything seems fine. I can proceed to cancel out this 1 here. But notice what the third row says. This one says that 0x plus 0y equals 3. Now what does that mean? Well, 0x plus 0y is 0. So this row is telling me that 0 equals 3, which we know very, very well is not a true statement. Now what does it mean when mathematics produces a false statement? Typically that means that the solution is not possible, that there exists no solution. So what I'm going to do here is I'm just going to pull up Wolfram Alpha and try to visualize these since these are in 2D. And what does this mean when we get a row like this? So I'm going to go back and plug in these equations. So just x plus y equals 10, 2x plus y equals 15, and x minus y equals 3. And let's see what that shows me. It should be an intersection point that I'm looking for. But you notice that if you look very carefully at this graph, that intersection point doesn't exist for all three. In other words, the purple line, 2x plus y equals 15, intersects with x minus y equals 3, but not simultaneously with x plus y equals 10. So it really forms a little triangle there in the center, and there's no common intersection point among three equations. Well, it should make sense because the second you throw in, pretend like that purple line wasn't there. Well, the blue and the gold line produce an intersection point, but the second you throw in a third line, what's the probability that the model, if it's not a coerced mathematical model, meaning we don't force it to intersect in the same spot, what's the probability that three lines all intersect in the same point? The probability is very small, and so now it can be the case, it can happen sometimes that they intersect in the same spot, what would happen in that case is if they did intersect in one spot, this row would clear out to be all zeros, just like it did back in our previous example where that fourth row popped out. And it would be possible still with 2 variables and 3 equations to get a solution, but most of the time we do get a false statement like this. And anytime your coefficients clear out but you have a non-zero constant, that's indicative of a non-existent solution. So we would conclude that there is no solution. And so we call this an overdetermined system because there are too many equations and there aren't enough variables, or more precisely, there is a fixed number of variables, but there are too many equations. So that's it. I know this video is a little bit long, but I kind of wanted to step through this in case you needed to pause it and see the exact steps that we were taking. So work column by column to get into that 1, 1, 1 across the diagonal, 0 everywhere else format.